Let us look at basic and applied physiology. Specifically, we're going to go over cellular fluids. Now, as we get to understand cellular fluids, well, I can also say body fluids because we are also interested not only in fluids which are found within the cells, but also those fluids which are found outside the cells. So when you get to consider the fluids in the body, they are going to be divided into those fluids within the cell and those which are outside the cell. So that is why we need to get to understand the body fluid compartments. All right. So when you are saying body fluid or cellular fluid, we are just talking about the fluid which is found in the body. Now, cellular itself, of course, is going to tell us about fluids which are found within the cells. But you've got also other fluids which are just found outside the cell. So we'll just refer to them as body fluids, right? So body fluids are going to be divided into two major compartments, or these fluids are going to be divided into two major compartments. So we're going to have the intracellular fluid called ICF. So the I is the intra. Okay, the C we are seeing comes from cellular, and then F, that's a fluid. Intracellular fluid. Now we know that intra means within. So this is a fluid that is found within the cell. And then we've got extracellular fluid, the fluid that is found outside the cell. Let's say you have got one cell here, and then the next cell here, and then let's say another cell here. We also have another cell here. So we are going to have the fluids which are going to be found within, okay, between cells. All the liquid that you are going to find, all the fluid that we are going to find around the cells, not inside, those are going to be called extracellular. And then the liquid or the fluid that we are going to find inside the cell, that is going to now be the intracellular. Now, when we get to consider the extracellular fluids, the fluids which are found outside the cell, they are also going to be further divided into the interstitial fluid, including also lymph. Lymph is the fluid that is found in the lymphatic system, just like we have got blood found in the circulatory system. We also have the plasma fluid, the fluid that is now found in the blood. Okay, we also have the transcellular fluid. Now, this is a special fluid. Well, in some books, we are going to see that transcellular fluid has been put to be part of the interstitial fluid. We are going to understand all this. All right, so we can now understand each one of those. So we'll start with the interstitial fluid. What is the interstitial fluid? So the interstitial fluid is the fluid that is found on the space between cells. So that is the interstitial fluid. So if you have got this as a cell, then another cell, any fluid that you are going to find on the spaces between these cells, that is going to be called as the interstitial fluid. And then the plasma fluid is the fluid that is found in the blood itself. All right, so that liquid part of blood is what we call plasma. And then the transcellular fluid is the fluid that fills up spaces of chambers that are created or formed from the lining of epithelial cells. So, for example, when you get to consider the eye itself, the eye, okay, let's say this is the skull, we have got these openings where the eyes are found. So we have got linings in those openings. So those linings, we call them epithelial linings or epithelial cells. Okay, just like also the digestive system. If you consider just the digestive system, just where the food is going to be passing, this lining is going to be covered by cells. Those cells, we call them epithelial cells. And now, that fluid that is covered or that is found in those spaces of those chambers, that is what we call the transcellular fluid. So we basically see that it is also outside what? That it is also outside the cell. That is why sometimes the transcellular fluid is going to be put under the interstitial fluid. So the transcellular fluid is going to include the peritoneal fluid, pericardial fluid, synovial fluid, pleural fluid, intraocular fluid, the CSF, which is the cerebrospinal fluid, and then we also have the gastrointestinal fluid, which is found in the digestive tract. All right, so here we are able to see the division of these fluids that we're talking about. We have got a cell here. So the fluid within the cell, that is the intracellular fluid, ICF, and everything outside the cells, that is going to be called the extracellular. So we have got this portion, which is in blue. This is going to be called the interstitial fluid. And then we have got this one, which is found within the blood. That is going to be called the plasma. Well, for here we cannot see the transcellular because the transcellular is found within some special cavities, like in the eyes, in the gastrointestinal line, in the GIT, let me say, within the intestines. We can also talk about the fluid that is just found below the, if you talk of the lungs, there are spaces in the lungs, the liquid that you're going to find there, that is also going to be called the transcellular fluid. All right, so when we get to look at this diagram here, we have got the peritoneal cavity. Remember we mentioned of transcellular fluid. So this is the peritoneal cavity that we're able to see. A cavity is simply a space. Okay, so this space, the fluid that is going to fill up this space, is what we are calling as a peritoneal fluid. Right? And then we have got, if we get to look at this person here, the second diagram, we have got the central nervous system. Now we have got, of course, these bones here, which the cerebral bones. Now we have got this space, okay, this space which is here. So the fluid that is going to fill up that is what we call CSF, cerebrospinal fluid. The fluid that is going to fill up that space in the central nervous system. We also have the heart. Okay, so the spaces within the heart, these spaces, now the fluid that is going to fill up that space is what we are referring to as the pericardial fluid. So these are examples of what transcellular fluids. They get to fill special uh, spaces. All right. After understanding the body compartments, intracellular and the extracellular, and how they are divided, we also need to understand some body electrolytes, because the body is going to have some dissolved ions within it. So those are what we call body electrolytes. So the body electrolytes actually makes up about 7% of body weight. That's the total body weight. So it means that if a person is 60 kg, the body electrolytes are going to be 7% of 60 kg. Okay, that is a space that they are going to be able to occupy. Now, for the body electrolytes, we've got sodium, potassium, the chloride, the calcium, magnesium, phosphorus, bicarbonate. These are the many body electrolytes. So, what's the function of the sodium ion? So the sodium ions are going to help regulate fluid balance, and they also aid, or they help in nerve and muscle functions. So when you're talking about fluid balance, you know that when you've got, let's say this is the this is the body, is divided into the intracellular fluid ICF and also the extracellular fluid ECF. Okay, you know when you have water here, you also have water here. Now, let's take it that in ICF we have got some sodium there. Okay, we have got some sodium ions. You know that according to the law of osmosis, particles or water is going to be diffusing from a region of low concentration to a region of, let me say, from a region of high concentration to a region of low concentration. Or in other words, they are going to be going in the direction that has got ions, right? The aim is to make sure that they get to dilute those ions. So you see water getting to flow like that in order to get to dilute those ions. But they are going to reach at a certain point where they are going to be balanced. So in the case when a person gets to vomit, for example, you get to vomit, some ions might get to remain. So there should be some balance that is going to be reached. Well, that is another thing that has to be understood in details when you get to talk about those types of solutions: hypertonic, isotonic, and hypotonic. So we'll get to understand that in detail. So they also get to help regulate fluid balance. Potassium helps also to regulate fluid balance. It also helps in nerve and muscle functions, right? So we also have the chloride ions, which help regulate also fluid balance. It also helps in maintaining a proper pH, right? You know that each when you have this body, you have got a lot of enzymes in our bodies, and so each enzyme has got its own specific pH that it works well at. So to make sure that the pH does not change significantly, you have got all these ions, chloride ions, that are going to make sure that they maintain a proper pH balance in the body. Because when the pH gets to increase beyond, well, some enzymes are going to be able to die. And those enzymes, when they get to die or when they are inactive, it means that some processes are not going to be able to happen well. We also have calcium, which is essential for health bones and teeth. It also aids in nerve and muscle contraction. We also have magnesium, which aids also in nerve and muscle functions. It also helps in regulating blood sugar levels. That is magnesium. Okay, blood sugar levels, very very important, because when the sugar levels are too high or too low, well, that is going to affect a person. We also have phosphorus, or the phosphate ion. So this one is essential for health bones and teeth, and it also helps in cell growth and repair. So as cells get to grow, or when cells get to die off, or something is getting to happen, for the cells to be repaired, there's need of phosphate ions. We also have the bicarbonate ions, which helps in maintaining proper pH balance in the body, and also are therefore a buffer system, meaning that they prevent significant change in pH in the body. All right. So when you're talking about extracellular and intracellular fluids, each of them have got their own values of ions and these other body electrolytes. So when you're talking about the extracellular fluid, that's the fluid found outside the cell, well, we are going to see that sodium is much higher. So sodium is about 142 milliequivalent per liter, and this table has to be mastered. It has to be known. All right, it has to be known by heart. So sodium in the extracellular outside the cell is much higher than inside the cell. So outside the cell, that is about 142 milliequivalent per liter, but inside the cell is just about 10 milliequivalent per liter. And then the potassium ion is much higher inside the cell than outside the cell. So inside the cell, there's about 140 milliequivalent per liter, and then outside is just 4 milliequivalent per liter. And for the calcium, well, calcium is more higher in the cell. I mean, outside the cell than within the cell. You can see inside the cell that is about 2.4 milliequivalent per liter, but out inside the cell, so outside 2.4, inside 0.001. That is like very low, approximately equal to zero. Okay, when you're taking, let's say, two significant figures, or let me say two decimal places. We have also the chloride ions. Now, the chloride ions are more higher outside the cell. And to be able to know this, just take it mostly where you get to find sodium, you get to find also the chlorine, because most of these are going to exist as sodium chloride. So sodium is about 103 milliequivalent per liter in outside the cell, and inside the cell that is just 4 milliequivalent per liter. We also have the bicarbonate. The bicarbonate ions are also more outside the cell than inside the cell. Outside we've got 28, inside we only have 10. We also have the phosphates. Now the phosphates are mostly found within the cell than outside. So outside the cell we've got only 4 milliequivalent per liter, but inside 75. We also have the sulfate. Sulfate is also a little more inside the cell than outside, though they are still low. Though the sulfate ions are still low, whether inside or outside the cells. Inside the cell, you have 1 milligram milli equivalent per liter, while inside you only have 2. Now, glucose is more outside the cell than inside the cell. So outside the cell, we've got about 90 milligram per deciliter, but inside the cell is about 0 to 20 milligram per deciliter. We also have cholesterol, phospholipids, and neutral fat. These are basically lipids. So lipids, we find that they are so low outside the cells, but they are much higher inside the cells. Outside the cells, about 0.5 gram per deciliter. Inside, 2 to 95 grams per deciliter. We also have the phosphorus dioxide, which is 35 millimeter of mercury. So this is the pressure because these are gases. Okay, so you are measuring them in the unit for pressure, millimeters of mercury. So inside the cell, the pressure of phosphorus dioxide is low as compared to outside the cell. When you get to look at the PCO2, you see that the pressure is a little bit higher outside the cell. I mean inside the cell than outside the cell. Well, we also consider the pH. The pH outside the cell is about 7.4. But inside the cell, it is neutral, that is 7. So meaning that outside outside the cells, the pH is a bit basic, right? Because 7.4, that is above the neutral pH, so it's basic. Now also have proteins. Outside the cells, the proteins you only have about 2 grams per deciliter, meaning that proteins outside the cells are much lower than inside the cells. So if you convert that to milli equivalent per liter, you're going to find that inside the cell proteins we only have 5 milli equivalents per liter, and outside the cells, like inside the cells, that is 40 milli equivalents per liter. So proteins are much higher inside the cells than outside the cells. So these numbers have to be known because you might be given a data collected from a patient and they ask you to comment on the results collected. Now, what are the major ions which are found inside the cell and outside the cell? So when you get to look at positively charged ions or cations for the inside of the cell, for the intracellular fluid, the major ones we have got the potassium ions and the magnesium ions. But outside the cell, you have got sodium ions. And then when you get to look at those which are negatively charged or the anions, for the intracellular fluid, you must have proteins and organic phosphates such as ATP, AGP, AMP. That is adenosine triphosphate, adenosine diphosphate, and adenosine monophosphate. So mostly these are the major anions, those which are negatively charged. But for the ECF, the major anions, we have got the chloride ions and the bicarbonate ions. Well, also have plasma proteins. You know that plasma is found outside the cell, all right? It is part of ECF. So the major ones, the major plasma proteins, we've got albumin and globulin, all right? So this table here just summarizes what I'm just from mentioning. When you get to look at the extracellular uh, fluid, those which are positively charged or the cations, you mostly have sodium. That is the most abundant. Of course, you have got some calcium, but it is so low. So the most abundant cation outside the cell is the sodium. While the most abundant anion, or those which are negatively charged, they are the chloride ions and the bicarbonate ions. You have got little proteins outside the cell, or even no proteins. And when you get to consider the intracellular fluid, you have got the proteins as a major anions and also organic anions such as the phosphate. Okay. And then for those which are positively charged, you mostly have potassium and also magnesium inside the cell. So these values are in many equivalents per liter. So we need to be able to identify which ions, cations or anions, are mostly found outside the cell and mostly found inside the cell. All right, so some conditions can arise when you have got these ions in excess or they are lacking. So when you have got low sodium or when you've got high sodium, so high sodium, that condition is going to be called hypernatremia. While low sodium, the condition is called hyponatremia. For potassium, high potassium, that is called hyperkalemia, and then low potassium, that is called hypokalemia. So hypo just means low, hyper means high. Well, high chloride ions, that gives a condition called hyperchloremia, while low is hypochloremia. When you talk of calcium, when it is high, the condition is called hypercalcemia, while when it is low, it is hypocalcemia. Magnesium, when it is high, the condition is hypermagnesemia. When it is low, hypomagnesemia. For phosphate, when it is high, that is hyperphosphatemia. When it is low, hypophosphatemia. For glucose, when it is high, that is hyperglycemia. When it is low, hypoglycemia. Now, since we said bicarbonates are mostly there to maintain pH, so that means that when you have got high bicarbonates, you are going to have what? High pH. When you have high pH, it means it's above 7. It is basic. And that is going to give a condition alkalolysis. Alkalosis. Okay. And then when it is low, that is going to give a condition acidosis. So this is alkalosis, acidosis when it is low, because you are going to have a low pH. So that is basically what we are saying. When pH is low, that is alkalosis. When it is high, when it is high, that is alkalosis because it's basic. When it is low, that is acidosis. And we also have HB levels. HB is just hemoglobin levels. When the hemoglobin levels are high, that is going to be called polycythemia. And when the uh, HB levels or hemoglobin levels are low, that is going to result into anemia because you have got low hemoglobin. All right. So another thing that we need to understand is total body water. Well, before I get to talk about total body water, maybe it will be easier for us to know how do you just get to know which ions are more. Why is it that you have got more of these ions within this and less of that? Of course, I'm going to talk about it as we get to go on. But we know that by the process of transcription, proteins are formed, and proteins are going to be formed. Well, transcription will first DNA is going to be converted into RNA. And then we're going to have translation, which is going to now form proteins from RNA. And this gets to happen inside the cell. That is why we're going to see that we have got more proteins inside the cell, in the intracellular fluid. And because proteins are big, they will not penetrate. You have got, this is a cell. And inside you have got a protein. So proteins are big. They will not be able to penetrate and go outside the cell. They do not penetrate the cell membrane. Rarely do they because they are big. So because they cannot do that, and you know that proteins are negatively charged, meaning that they are going to be pushing away those substances which are negatively charged and they are small. That is why the chloride ions, they are going to be pushed outside the cells. They find themselves in the extracellular fluid. And because of that, to maintain the positive and negative charges within the cell, the proteins which are negatively charged are going to be attracting those and the cations, those which are positively charged. That is why you get to see they attract more of the potassium. So we're going to have higher potassium inside the cell, and low calcium chlorine because the chlorines have been pushed away. Now you also know that when the chlorines are pushed away outside the cells, well, most of the chlorine is supposed to come or be together with the sodium. That is why the chlorines also are going to be attracting the sodium. So you have got more sodium outside the cell. All right. Now we also know that when you have got high potassium, the potassium can also attract the phosphate ions for potassium phosphate. That is why I also expect to find some more of phosphate ions inside the cell. So just this explanation just to help us get to understand why we have got more of this inside the cell and less of this. Now let's get to understand also total body water. And we're going to concentrate more on a 70 kg adult male. Alright. So total body water is just the water that is found within the body. Now, we need to know that the total body water, TBW, in a 70 kg male is 60% of total body water. Now, the 60% is not just in a 70 kg male. Actually, for the body, like for a male, 60% of the weight of a male is made up of water. So, meaning that if a male is, let's say, a male is 70 kg, you are going to multiply by 60%, which is 60 out of 100. And this is going to give us 42 kg. All right? It's going to give us 42 kg. Now, you know that the density of water is 1 kg per liter. So, if it is 1 kg per liter, meaning that if you have got 42 kg, it means that the volume is also at 42 liters. So, that is why for a 60 kg, for a 70 kg adult male, you have got 42 liters of water in the body. Okay, so this is the total body water. So if you change the mass of the person, for example, most of the females, because if we get to consider, we have got some things that get to affect total body water, like sex. Males, you have got 60% of body weight. Now for females, it's just 50% of body weight. Why? Because the other percentage is going to be taken by electrolytes. So that is where the other percentage of body weight is going to go. Females are mostly fat like that, or they get to store a lot of fat within their bodies. That is why they are going to have reduced body water. So if you are talking about a female, let's say who is 80 kg, to find the total body water, you're going to multiply by 50%, and that is basically 50 out of 100. So this is just going to be basically half of 80 kg. That is going to be about 40 kg. And we know that the density is 1 kg per liter for water, meaning that for an 80 kg woman, the water is going to be 40 liters in the body. So another thing that gets to affect total body water is the age of the person. And mostly for children, water is much higher, about 75% of body weight in children as compared to adults. So children have got more water than adults. All right. So now, how is the distribution of total body water in the body compartments, in the ICF, in the ECF, and also just dividing the ECF? How is water distributed? Now, when you consider for a 70 kg adult male, that is what we are going to be using. We've already said that the total body water is 42 liters from the calculation that we have already seen. Now, ICF, most of the water is found within the cells, and that is actually 2/3 of total body water is found within the cells, right? So 2/3 of the water is found within the cell. So what you are going to do is to find the volume of water found within the cell. That is 2 out of 3 of total body water. And you know that total body water is 42 liters. So that is going to be 2 out of 3 of 42 liters. So I'm going to find that 28 liters of the water is within the cells. And for outside the cells, or if you want, you can just say 42 minus 28. That is going to give you outside the cells. But 1/3 of the total body water is outside the cell. That gives us now 1/3 times 42, which gives us 14 liters. Now we've seen that outside the cell we have got 14 liters. But outside the cell, we know we have got the plasma fluid, the interstitial fluid, and the transcellular fluid. But in this case, we're going to take the transcellular fluid to be part of the interstitial fluid. So we'll just divide into plasma and interstitial, the ECF, the extracellular fluid. Now, from the 14 liters, plasma takes up 41 out of 4 of the ECF. So a quarter of the extracellular fluid is plasma. So you know that ECF is just 14 liters. So that will be 1 out of 4 of 14. So we're going to find that plasma is about 3.5 liters. So the liquid found within the blood is about 3.5 liters. And then the interstitial is going to be 3 quarters. So that is 3 out of 4 of the extracellular fluid, and that is 3 out of 4 of 14 liters, which is 10.5. Now we need to know that this 14 we are using is always for an adult 70 kg male. So this value will not be the same when you're talking about someone who is 80 kg or someone who is female. You have to calculate, to go back and say 60% of, for example, if you are still talking about a male but is not 70 kg, maybe 80 kg, you say 80%, 80 kg times 60%, that is going to give you the total body water. And then you have now to find the extracellular fluid, which is about 1/3 of the total body water. When you find that, that is the value that you are going to come and use here as the ECF. So this one is for a 70 kg adult male. Now, remember, we have said plasma is 1 out of 4 of ECF, but we also know that ECF is 1/3 of the total body water. Meaning that if you've been given the total body water, you can find the volume of plasma by just saying 1/12 of total body water. And the interstitial fluid, you said it is 3 out of 4 of ECF. And ECF, we said, is 1 out of 3 of total body water, meaning that this will cancel with this, meaning that interstitial fluid is just 1 out of 4 of total body water. When you get to add 1 out of 4 of total body water plus 1 out of 12 of total body water, this will give you back. I can multiply on top by 3, down also by 3, just to make the denominators the same. So it will give us back 4 out of 12, which is 1 out of 3 of total body water. So when you get to add this and this, you are going to get 1 out of 3 of total body water, meaning that plasma and interstitial fluid, when you get to add them, they should give you ECF volume, which is 1 out of 3 of total body water. So in case you've been given total body water, you want to find plasma or interstitial, you can get to use that formula, or you can first find ECF and then you'll be able to calculate the others. Now, just as we said earlier, solutes and water can move between the plasma and the interstitial fluid. For example, you have got, this is the blood vessel, and then this is a space outside the cell. So basically, everything that is found inside the blood and outside the cells, the composition is the same. The only difference is because of the same plasma proteins. Okay, so negative plasma proteins are too big to cross the pores. You know, proteins are supposed to to move from the blood going outside the cell or in the interstitial fluid and back like that. But because the proteins are that big, it is not that easy for them to be able to cross or to penetrate these pores. That is why you're going to see that the concentration is going to be much higher at a certain region for the proteins because they are big. So where the proteins are found, that is where they are going to be highly concentrated, just like they are more in the ICF than ECF. Why? Because proteins are found within the cells. We know that they are formed by translation, and translation happens inside the cell. So expect them to be found within the cell more because they cannot penetrate and go outside the cells because they are big. So since we are saying that negative proteins are too big to cross, okay, between plasma membranes and the interstitial fluid, how do we maintain neutrality because proteins are negative? Well, because proteins are negative, as we said earlier, they are going to be attracting small positive ions, as they are also getting to pull away those which are negatively charged, because they are also negative. So because of that, proteins which are negative, they are pulling positive things around them and then pushing away negative things. So that is how they are going to be able to maintain neutrality, and that is called the Gibbs domain effect. So that is basically what we are calling as ultrafiltration. So we're going to say that when you have got more of proteins here in the plasma, it will be very difficult for it to penetrate or go into the interstitial fluid, and so it will maintain its position there, and so it will just be attracting those ions which are positively charged. That is why we're going to say that slightly the composition of proteins in the plasma is going to be higher than in the interstitial, even if both are outside, they say, or both are found in the extracellular. So interstitial fluid has more anions like chloride. So we're going to find more chlorides here. Why? Because we've got more proteins within the cells, and those proteins are pushing away these chlorides, not within the cells but within the blood vessels, and so those proteins are pushing away the chlorides, and then the blood plasma has more cations. Why? Because the proteins are attracting those cations like the sodium. So in case you get to notice some few significant differences, well, between the interstitial and the plasma, it is because of ultrafiltration. Now, how do we get to measure the volume of the fluid compartments? Well, the method that we get to use to measure the volume of the fluid compartments is called the indicator. So indicators we use are dye, so it is called the indicator or dye dilution method. And basically the one we are going to use here is the Stewart Hamilton dye dilution method. We are going to understand this method will just tell us about, an equation that is going to help us understand this. But the method itself we use is the dye or indicator dilution method. So some indicators that we get to use when you want to find the total body water that is found in the body, you are going to use D2O. That is, this is just an isotope of normal water H2O, but you don't use the normal hydrogen. You use an isotope of hydrogen. So when you get to inject D2O, it is going to go to any position or any point in the body that contains water. So it's going to label any point, and then you are going to be able to find out the total body water. Now, when you want to measure ECF volume, how much volume is outside the cell, you are going to inject mannitol or sucrose. Now, the reason as to why we use mannitol or sucrose to measure ECF is because these are not able to penetrate into the cells. They are not able to cross the cell membrane. For example, this is your hand. You are injected with mannitol or sucrose. Well, it will just be outside the cells, but within the hand, it will not go inside the cells. Why? Because it cannot penetrate or cross the cell membrane. So mannitol and sucrose is going to only label every fluid which is found outside the cell. Now, to measure the fluid which is found in plasma, we are going to use Evans blue. Okay, Evans blue is going to be able to measure the fluid which is found in plasma. That is more because it gets to attract. It is attracted to the plasma itself. All right. Now, to be able to measure the volume, as we said, the method that we mentioned there, the Stewart method, this is a formula. So the volume of any compartment is going to be equal to the amount that you injected minus the amount that you've excreted divided by the concentration. For example, if you injected, let's say, 20 grams of mannitol, and then 10 grams of was removed through urine, and then the concentration of the mannitol which remained, let's say, maybe 0.1 gram per milliliter. So you can find now the volume of the extracellular fluid. So you need to know that every time they're talking about mannitol or sucrose, that is talking about what? Then what they are trying to measure is ECF. You also are able to measure blood volume by just saying blood volume. So blood volume is given by plasma volume divided by 1 minus hematocrit. Now, hematocrit is simply the percentage by blood of red blood cells in your blood. How much red blood cells are there in the blood? That is what we call hematocrit. Right. So we have indirect methods of measuring volumes and direct methods. So for direct methods, you are able to measure the total body water because there is a dye that you are able to use. You've seen the dyes which we mentioned. You are also able to measure ECF, plasma volume, and also blood volume by direct methods because there are dyes which are able to label this. But you don't have dyes that can go into ICF minus them passing through ECF, and there is no dye that is able to measure interstitial fluid. So that means that if you want to measure ICF, you first need to know the total body water and then you remove ECF. And then you're going to be able to determine ICF. If you want to measure the interstitial fluid, then you first need to know ECF. When you remove the plasma, then you are going to remain with the interstitial, the interstitial fluid volume. So these are other indicators that you're able to use, and these ones we need to know them because different questions are going to come. They've just given you indicators which were injected. They ask you to find volume. So if you don't know that this indicator uh, is able to label this, then you are not able to answer that. So when you want to find the volume in the plasma, you are able to use albumin. Okay, that is iodine albumin, or you are also able to use Evans blue. The reason is they cannot cross the capillary membrane. So when you inject them in the blood, they are not able to move outside the blood vessels. All right. So that is why they are used. If you want to measure ECF, that is the plasma volume plus the interstitial volume, that is ECF, right? You can use sodium 22 or iodine. You can also use thiosulfate or inulin. The others you are able to use, those are the ones we mentioned, mannitol and also sucrose. So to measure interstitial fluid, you can't measure it directly. So you use an indirect method. That is, you first find ECF, you also find the plasma volume, and then you subtract them. Now to measure the total body water, that is ECF plus ICF, you can use antipyrine heavy water, D2O, that is D2O heavy water. Okay, these are some things that you're able to use. Antipyrine or heavy water. So you get to inject them. So that is going to measure the total body water. And then to measure the intracellular fluid, there is no direct method. You use the indirect method. First measure the total body water and then minus ECF. To measure the blood volume, we're able to inject chromium labeled red blood cells, or blood volume is equal to plasma volume divided by 1 minus hematocrit. So if you don't use the chromium labeled red blood cells, you can use the formula. First, you have got blood volume. First, you find the plasma volume, then you divide by 1 minus hematocrit. So that is how you're able to work out this. So we also have what is called plasma osmolarity. Plasma osmolarity. Well, we need to understand there's also a difference between osmolarity and osmolality. Just like there's a difference between molarity and molality. So there's also a difference here. So this is osmolarity. There is an R here. And for osmolarity with an R, this is going to tell us about the number of osmoles divided by the liters of solution. But if there was L here, that would be the number of osmoles divided by the kgs of solution. Just like molarity is moles per liter, but molality is moles per kg of solution. Where there's L, you talk about kgs of solution. So this is also what we need to understand. We have also mentioned osmose. So osmose is simply the unit that you get to use when you're talking about the concentration of osmotically active particles. So those particles which are able to move by osmosis. So this is the formula that gives us the osmotic, the plasma osmolarity. So plasma osmolarity is given by 2 multiplied by the sodium ion concentration plus glucose divided by 18 plus BUN divided by 2.8. So the BUN, that is blood urea nitrogen. So all those values are going to be given if they ask you to calculate plasma osmolarity. Well, let's look at some practice questions to see if we have really understood this tutorial. Calculate the percent distribution of fluids between various body fluids compartments for a 105 kg person, knowing the water or fluids in each of the following body up. The question was also not well punctuated. Calculate the percentage distribution of body of fluids between various body fluid compartments for a 105 kg person, knowing the water or fluid in each of the following body approximate volume of your. Wow, this question is confused. So basically what it was talking about is you want to calculate the percentage distribution of body fluids between various body fluid compartments for someone who is 105 kg person. Now we've not been told the gender, and this we are going to use a male. So knowing that the fluid in each compartment is going to be distributed as we know, okay, as we know. So we need to know that this percentage is for ICF, this percentage is for ECF. Now you need to show all your working to N for max. So starting, we're going to first calculate the total body water, and you know that total body water, we are using a male, it is 60%, which is 60 out of 100 times the mass times the body weight, that is 105. So 60 out of 100 times 105, this is going to give us 63 kg, which is equal to 63 liters. So this is the total body water. Okay, we also know that when we know the total body water, ICF, that's the intracellular fluid, is 2/3 of total body water. So that is going to be 2/3 of total body water, and the total body water here we have 63 liters. So 2 out of 3 times 63 liters, then that is going to give us 42 liters. And then we can also calculate ECF, and you know that ECF is basically 1/3 of total body water. So that is going to be 1 out of 3 times total body water, which is 63, and that is going to give us 21 liters. We also need to calculate the plasma volume, and you know that the plasma volume is 1/4 of ECF. So this is going to give us 1/4 of ECF, and the ECF volume will determine 21 liters. So this is going to be about 5.25 liters. And then we can also calculate the interstitial volume, and that is basically 3/4 of ECF. So this is going to be 3 out of 4 multiplied by 21, and that is going to give us about 15.75 liters. So that is how we're able to work out this one. The next one here. A 70 kg man is injected with 150 millicurie of D2O. So a curie is simply a unit of radioactivity. So millicurie of D2O and 650 milligrams of mannitol. Now we need to know, when we're talking about D2O, what are we trying to measure? Well, this is total body water. What of mannitol? This is ECF volume, right? So during a 2-hour equilibrium period, he excreted 10% of mannitol and 10% of D2O in his urine. After that, the concentration of D2O in the plasma is 0.32 millicurie per 100 mils, and the concentration of mannitol is 4.6 milligram per 100 mils. We want to calculate the total body water, ECF, and ICF volume. So starting with total body water, well, we know that this is a 70 kg person, but since we've been given what was injected, so we're going to use a Steward Hamilton dilution method. And that one, total body water, we know is going to be given by the amount divided by the concentration. Amount is also given by amount which was injected minus the amount which was excreted. And then you divide now by the by the concentration of the same substance which was injected. Now we know here to measure total body water we use D2O. So what is the amount which was injected? 150 millicurie was injected, so that would be 150, okay, minus how much was excreted. We've been told 10% of D2O was what? Removed via urine. So that is what was excreted. So we are saying what was excreted is 10% of what was taken in. So that is 10 out of 100 times what was taken in is 150. This is also in milli curie divided by the concentration. So I've been told that the concentration of D2O in the plasma is 0.32 millicule per 100 milliliters. So all we are going to do here is to get to punch this on the calculator. So 10 out of 100 multiplied by 150, and then that value you get to subtract from 150 and then divide by 132 millicurie divided by 100 mils. So if we want to go with it stepwise, if we say 10 over 100 multiplied by 150, that is going to give us 15. 150 subtract 15, that is going to be 135 millicurie divided by, down you have got 0.32 millicurie per 100 mils. So what I'm going to do, I'll say 0.32 divided by 100. That is going to give us, just a moment. So that is going to be 0.0032. This is going to be in millicurie per milliliter. So you see that this unit and this unit is going to cancel out. So the answer is going to remain in milliliters. So you can now divide 135 divided by the answer in the denominator. That is going to give us about, this is going to be 42187.5 milliliters. So I'm going to convert this to liters. So just divide by 1000. So the decimal point is going to move from here 1, 2, 3 times. So that is going to be about 42.2 liters. So this is the total body water, 42.2 liters. And then we can also find the volume of ECF. So I'll just change here ECF. Well, we know that when you are measuring the volume of ECF, what you get to use is what? What you get to use is mannitol. So the mannitol which was injected at the beginning, let's take note of this value 42.2 which I found down here. So the formula still remains the same. But in this case, we are now going to say amount which was injected, the amount which was injected, that is 650 milligrams, minus the one which was excreted. We've also been told 10% was excreted. So that would be 10 out of 100 multiplied by the same which was injected, which is 650, then divided by the concentration of the mannitol. So the concentration of the mannitol we've been told that is 4.6 milligrams per 100 milliliters. So when we get to use also the same formula that we used, we're going to just punch this on the calculator. We're going to get 12,717.39 mils. And this we convert to liters, just divide by 1,000. So that is going to be 12.7 liters. We have found ECF. So to find ICF, we said ICF use the indirect method. ICF is given by total body water minus ECF. And the total body water we found 42.2, and then ECF we have found 12.7. So that is going to give us about 29.5 liters. So that is going to be the ICF volume. All right. Let's consider question 3. The following are transcellular fluids except we have got cerebrospinal fluid, aqueous humor, synovial fluid, plasma. Well, we know that the transcellular fluid is the fluid that is found on portions which are covered by the epithelium, like the cerebrospinal fluid, aqueous humor, the fluid found in the eye, synovial fluid, the fluid which is found on joints, like on the knee and elbow. Now, plasma is not part of transcellular. We know this is another type of just extracellular fluid. So that is it. Concerning electrolytes, which one is true? Potassium ion is the main cation of ECF. Bicarbonate is higher in ECF than ICF. Proteins are higher in ECF. Sodium is the main cation in ICF. Which one would you choose? So as we said, in ICF, we have got more proteins. Because we have got more proteins, we are going to push away other negative things. So other negative things are going to find themselves in the ECF. For example, what negative things are we able to mention? The chlorine, the chloride ions are going to be found in ECF. Now proteins, because of that, they are going to attract those which are positive, like the potassium ions. As we also mentioned, when the chloride ions are pushed into ECF, they're going to attract those which are positive also, like the sodium ions. So the major cation in ECF is not potassium but sodium. So this option is wrong. Sodium is the main cation of ICF. We can see sodium is more in ECF. This is wrong. Proteins are higher in ICF. We know that proteins are higher in ICF, not in ECF. Bicarbonate is higher in ECF than ICF. Well, we mentioned bicarbonates are higher in ECF. We said they are one of those major anions in ECF, the bicarbonates, right? So this is going to be it. Bicarbonate is higher in ECF than in ICF. We can just refer to this. There is something that I'm also getting to think about this one. So from what we're able to see here, we can see the bicarbonate ions, they are there more on the what? On the ECF. So that is why I said this slide also has to be known, the major anions and cations. So bicarbonate more in the ECF. All right, and then we've got question number 5. 100 milligrams of sucrose is injected into a 70 kg man. The plasma level of sucrose after mixing is 0.01 milligrams per mils. If 8 milligrams has been metabolized during this period, then what is the ECF concentration? Now we know that when we are talking about sucrose, sucrose gets to measure ECF concentration. Therefore, this means that ECF is going to be the amount which was injected. We've been told 100 milligrams was injected minus that one which was metabolized, or the one which was what? Which was excreted, and 8 milligrams was excreted or metabolized, divided by the concentration. We've been told the concentration is 0.01 milligrams per milliliter. So when we get to punch this on our calculators, we are going to find 9,200 milliliters, because this is in milliliters. But we need the answer in liters, so divide by 1,000. We're going to find that that is 9.2 liters. So that is 9.2 is this one here. Okay. So that is going to be it. And then we can also look at this one. A physiological experiment is conducted to calculate various body fluid volumes. The proposed method to be used was to slowly infuse a dye indicator into a 70 kg man's blood, and after allowing equilibration, to measure the concentration of the dye in plasma. The indicators were infused as follows. 250 mils of radioiodinated albumin was infused. Plasma radioiodinated albumin concentration was detected as zero point 0.1 milligrams per mil. So we need to know what the iodinated albumin measures, whether ICF, ECF, total body water, plasma, interstitial. We mentioned this. And then 200 mils of sucrose was infused. Plasma sucrose concentration was detected as 0.01 milligrams per mil. During equilibration, 50 mils of sucrose was metabolized. Now, if we can see what is happening here, well, for the iodinated albumin, we've seen that nothing was excreted. So when you are finding the volume, it will just be the amount divided by the concentration because we don't have anything which was excreted. And for albumin, this one you get to use it when you are calculating the plasma concentration albumin. And then for the sucrose, we said this one is used when you are calculating what? When you are calculating the amount of ECF or the volume of ECF. So take note, this was injected and then this was excreted. For this one, there's nothing which was excreted. All right. Now, what are the questions which we have? The first one, what name is given to the method using the experiment above to calculate fluid volumes? So the method is dye or indicator dilution method, right? And then the next one, calculate the following body fluid volumes. First one I want to calculate is extracellular fluid. The next one, fluid volume, and then the interstitial fluid volume. And then question 3, if the man's hematocrit was zero point 0.5, calculate the total blood volume. All right, so I'm going to get a blank page. For question 2, I want to calculate the extracellular, plasma, and interstitial. So starting with the extracellular volume, ECF. So ECF, we're going to say the amount which was injected minus the amount which was excreted, and then we're going to divide that by the concentration of the sucrose which was injected. So the amount which was injected from what we have seen, what we've been given, this is ECF. Let me just refer to it again, what we've been given. So 250 mils of radioiodinated albumin was infused. So for the plasma, okay, for the sucrose, plasma sucrose, 200 was infused and then 50 was excreted. And we know that sucrose is used to determine the ECF. So that is going to be what was infused, that was 200 milligrams, minus what was excreted, that was 50 milligrams, and then we divide by the concentration which remain, that is been given as 0.01 milligrams per milliliter. So punching this on our calculators, we're going to find 15,000. The answer is going to be in milliliters because we have got milliliter down here. So we need it in liters, divide by 1,000, that is going to be 15 liters. And then the next one, they asked us to find the plasma volume. So the plasma volume, when we use iodinated albumin, we didn't have anything which was excreted. So just the amount divided by concentration. And the amount, what we've been given is 250 milligrams, divided by the concentration, that is zero point 0.1 milligrams per milliliter. And that is going to give us 2,500 milliliters, which divided by 1,000 is going to give us 2.5 liters. The next one we've been asked is to calculate the interstitial fluid volume. And you know that for interstitial fluid volume is just ECF minus plasma. So the ECF we've calculated 15 liters. The plasma we have calculated 2.5. and that is going to give us, all right, that is going to give us about, is it really, let me see what the question was asking us to calculate. Okay, that is interstitial, that's true. Okay, so for the interstitial, we're going to get to subtract this 15 minus 2.5. So that is going to give us 12.5 liters. Okay. So this is it for this question. Also, that's for question B. Let's see question C. Question C. If the man's hematocrit was 0.5, calculate the total blood volume. Now remember we said to calculate hematocrit, to calculate the blood volume, let me say BV, blood volume is given by plasma volume divided by 1 minus hematocrit. So the plasma volume we've already calculated as 2.5. And then divided by 1 minus hematocrit is given as 0.5. So this is going to give us 5 liters. So this is the blood volume of this patient. And then the last one here. Using your knowledge in cellular fluids, explain these blood results obtained on a 30-year-old male patient who was admitted at UTH Ewards. So the blood test results showed sodium concentration being 97 milliequivalent per liter, potassium greater than 10 milliequivalent per liter, chloride 86. Meaning that for us to be able to answer these questions, we need to know this table by heart. Now, since this was blood which was collected, and you know that blood is what? Extracellular. Okay, it's part of the extracellular fluid. So we're going to be comparing these results with the normal results. We know that sodium in the extracellular fluid, the normal is supposed to be 142 milliequivalents per liter. And then for this potassium, we know that is supposed to be 4. Okay, so I'll just put this here. And then for the chloride, that is supposed to be 1.103. That's the normal one. Okay, so I'll also put it here, 103. And then for the calcium, we have 0, but the normal one is supposed to be 2.4. And then magnesium, the normal one we are supposed to have is supposed to be 1.2. If you look at the phosphates, the normal ones which are supposed to be present, that is 4 milliequivalents per liter. And then for glucose levels, the normal one is supposed to be 90 milligrams per deciliter. And then the bicarbonate ions, the normal bicarbonate concentration, that is 28 in ECF. And then the pH in ECF, the normal is supposed to be 7.4. HB levels, of course, on this table is not there. But the normal HB levels are supposed to, the value is supposed to lie for males, since this is a male, the normal value is supposed to lie like between 13.8 to 17.2. So now let's comment on these results observed. So we have seen that the sodium levels were so low. So what condition is this when the sodium levels are low? So we need to refer to also the conditions which the person is going to be suffering because of those low sodium conditions. So since that the sodium is low, that is hyponatremia. Okay, so this person is going to have hyponatremia because of low sodium. And then if you go to potassium, potassium is what? Is also low. That means that this person is suffering from, actually potassium is high because it's greater than 10. The actual is supposed to be 4. This one has got hypokalemia. Hyperkalemia because it's high. Okay. And then the chloride we can see is low. So that condition also we need to comment what condition. So same, we also look at calcium, magnesium, phosphate, glucose. So the conditions are already there. So to comment, you want to what? You want to just comment using your knowledge, explain these blood results. So are they normal or not? So that is what you want to explain. If a person is sick or they are within the normal range, what condition they are going to have because of these results that you are able to see here. So that is how we are going to be able to answer this question. So meaning that for the next this table here, we have to know the values, because without knowing this, you are not able to answer the previous question on commenting on the results. Well, thank you so much for watching. Hope this was helpful. Please remember to subscribe and also be able to like and share. Stay